Hello everyone, and thank you for watching this presentation. My name is Michael Kogan, and for the next 10 minutes I'll be talking to you about my work, done under the supervision of Dr. Travis Desell, titled Self-adaptation of Neuroevolution Algorithms using Reinforcement Learning. I will start off with a brief overview and then introduce EXAMM, a neuroevolution framework. I will outline the problem statement and talk about Fala, a reinforcement learning algorithm. I will talk about how we can apply Fala to EXAMM, describe our experimental approach, present the results, and conclude the presentation. So, neural networks are very powerful models, largely due to their flexible architectures. However, this also makes them very difficult to design, which has led to the study of automated approaches. One class of algorithms called neuroevolution has shown great promise in automating the neural architecture design process. These algorithms can generate architectures that are different from their human design counterparts and have demonstrated the ability to outperform even the best man-made networks in certain datasets. Unfortunately, they do tend to have a large number of mainly tuned hyperparameters, making them somewhat inaccessible. One such algorithm is known as EXAMM, and it was developed at the Rochester Institute of Technology to evolve recurrent neural networks. It has proven to be especially useful for multivariate time series data. At the core of EXAMM is a master process that maintains a population of candidate genomes distributed across a certain number of islands. Each island contains an identical number of genomes, and each genome consists of a neural architecture along with an associated fitness value, which is calculated based on its test set performance. All of the islands are initially populated with slight variations of the baseline genome, which is a very simple two-layer fully connected network. As the algorithm progresses, ever more complex architectures are evolved. In order to generate a new genome, the master process will first select an island in a round-robin manner, and will then select a genome at random from that island to evolve. It will do so using one of the genetic operations listed on the right, selected in accordance with their probabilities, and will train that genome on one of the worker nodes for a certain number of iterations. It will evaluate the newly trained genome on the test set to determine its fitness value, and will reinsert it back to its parent island if its fitness is superior to that of the worst genome in that island. We have identified several problems with this approach and developed solutions to address them. Certain genetic operations may be better than others, and these will change over time depending on the current state of the population. As such, we should dynamically adjust the genetic operation probabilities to favor those that are currently performing well. Furthermore, cycling through islands in a round-robin manner may not be optimal because the populations of the islands tend to become heterogeneous over time. As such, we should select islands in accordance with an evolving probability distribution that favors those islands that have strong populations. Lastly, there's a large number of mainly tuned hyperparameters, and so we should explore techniques that have few hyperparameters that can automatically adjust the large number of underlying hyperparameters that are currently manually selected. The approach that we chose to address these concerns is called Fala, or finite action set learning automata. It is a reinforcement learning algorithm and has four main components. The first one is a finite set of possible actions, called alpha. The second is an evolving probability vector, P of t, which corresponds to the probability of selecting each action at a given time step t. Now, the action selected at time step t is usually called alpha of t. Next, we have a reinforcement function r, which will observe the results of the action taken at time t and generate a reinforcement signal r sub t. Lastly, we have a learning function tau. It will update the action probability vector such that p of t plus 1 is equal to tau of alpha of t, p of t, and r sub t. When you put these four components together, you have a single Fala learning process, usually called gamma. The number of hyperparameters here is equal to the number of parameters in tau and r. In the baseline scenario, it's just 1, but we may choose to increase the number of parameters to better control the evolution of the probability vector P of t. In its baseline form, Fala will always converge to a single action. However, in the context of neuroevolution, this is not desirable because good networks are evolved using a combination of different genetic operations. We can apply several techniques to prevent this from happening. The first one is to place a floor in the values of the action probabilities. The second is to apply negative reinforcement, potentially only after a certain degradation threshold is reached. The third is to use proportional reinforcement, and the fourth is to use staged learning, where we break up the learning process into a series of stages and reset the probabilities at the end of each stage. Now that we have a good understanding of what Fala is, let's talk about how we can apply it to EXAMM. The dynamic adjustment of genetic operation probabilities maps naturally. We have our action set and we have our initial probability vector. All we have to do is layer on the reinforcement signal and learning function and we're ready to go. In the case of island selection, we had to rework it so that we're no longer using the round-robin approach. Instead, we have a sampling-based approach. The action set is the set of all possible islands, and the probability vector is initialized to be 1 divided by the number of islands for each island. We also introduced an additional reinforcement component for the island that has the best genome in order to make sure that island is always reinforced a little bit. In order to test our solution, we developed 3 different learning configurations and used 10 runs per configuration. The first one was just the baseline EXAMM algorithm. The second one was a slower learning approach where we would adjust the action probabilities more slowly, but also had fewer stages to reset them back to their initial values. The last one was a faster learning approach where we would adjust the probabilities more aggressively, but had more stages. We had 5 islands with 5 genomes for a total population of 25 and a genome limit of 2000, meaning we would stop each run as soon as 2000 genomes were generated. The best genome from each run was recorded, as was the evolution of all action probabilities, and we used the coal-fired power plant dataset for all runs. This dataset has been used previously for different EXAMM studies and is therefore a fitting dataset to use for this one as well. On the left-hand side of this slide, you can see the test set mean squared error distribution of the runs stratified by learning configuration. Visually, we can tell that the slow learning configuration was better than the other two, although the medians of the slow learning configuration and the fast learning configuration were actually quite close. We also did pairwise comparisons between the populations of the different configurations, and what we found was that the difference between the baseline configuration and the slow learning configuration was statistically significant at p equals 0.05 when compared using the man-Whitney U-test. What this proves is that our approach did indeed improve the performance of the baseline algorithm. On this graph, you can see the evolution of genetic operation probabilities from the best runs. The slow learning configuration is on top, and the faster learning configuration is on the bottom. You can tell the difference between the two based on how much more aggressively the probabilities evolve in the faster learning configuration. Now, while some operations are reinforced more frequently than others, no operation completely dominates, showing that our convergence prevention techniques did their job. Of the operations that are reinforced, the disable edge operation was most surprising to us. Intuition would suggest that disabling edges would reduce the complexity of the network, and therefore reduce its performance. However, it turns out that disabling edges may act as a form of regularization, which is critical to preventing overfitting, and therefore results in better test set performance than initially anticipated. On this slide, we can see the island selection probabilities from the best runs. The slower configuration is on top, and the faster configuration is on the bottom. We can tell the difference between the two based not only on how aggressively the probabilities evolve, but also based on a number of stage transitions. Each time the probabilities are reset back to their initial values, we can see a stage transition. We can count 9 of those at the bottom and 3 of those on the top. What we note here is that 1 or 2 islands are consistently reinforced, while the remainder are seldom reinforced. What this proves is that Fala is able to identify and promote those islands that have the most promising genomes. We can contrast this observation with the evolution of the island selection probabilities from the worst runs, from the slower and faster learning configurations. What we see here is that no island is consistently promoted, and what this tells us is there's fewer non-promising genomes amongst the population. And this actually gives us some insight into the performance of the algorithm as a whole. What we notice is that the initial conditions are good, or the seeding of the islands is good, then there will be promising genomes which can be picked up and reinforced throughout the learning process. However, if the seeding is poor, then we'll get a situation like this, where there are no promising genomes, and the Fala algorithm is unable to pick up any good islands as a result. To conclude, this work demonstrates that reinforcement learning can be successfully applied to guide EXAMM's neuroevolution process. Fala integrated into the base EXAMM framework with relative ease, and the results demonstrated statistically significant improvement over the baseline approach. 5 hyperparameters are required for each Fala learning process, and this can be reduced through further optimization. For mutations, the original number of hyperparameters to tune was 12, so we're demonstrating a significant reduction in how much work the programmer has to do, thereby making these types of algorithms more accessible. Furthermore, we open up avenues for future work. We can apply Fala to other neuroevolution approaches, such as NEAT, and we can attempt to intelligently select genomes from each island. Currently, after an island is selected, the genome to which to evolve is selected at random. Maybe there's a way or an approach to select these genomes more intelligently to further improve the performance of this algorithm. Thank you for your time. I hope you enjoyed this presentation, and if you have any questions, please feel free to reach out.